One of the reasons that things in complex analysis seem kind of topsy-turvy is because they both depend on simple ideas from real analysis or even from calculus, and then they have these wide-ranging implications when you change them into the complex plane. So one of the things that we get here is the open mapping theorem. An open mapping is one that takes open sets to open sets, and that has very profound consequences if you know that a mapping is open. And basically, every non-constant analytic function or holomorphic function is an open mapping. This is the corollary to Theorem 11 in Alfors. And the way this starts is with something super simple from calculus. We're going to take the first thing that you do in calculus, which is the ordinary parabola y equals x squared. Nothing fancy, just ordinary y equals x squared, and we can graph that, and it has, at the vertex, it has a double zero. There are two zeros there. Another way of saying that is that if we move away from zero a little bit and we want to solve x squared equals a, well then what happens is we get two distinct roots, and that would generally be the case. And so the root with multiplicity is a special case here, but if we move away a little bit, then we get two distinct roots, and we can work with those kind of separately or together as needed. So we would like to translate this into the complex situation. It's going to be more complicated, but it's also going to end up having this amazing consequence. So the thing that we have to take advantage of, let's kind of set up our domains. We're in a disk capital delta, and inside that we have some simple closed curve gamma. And so this is the domain of our function f, and f is analytic. And so what we got as a consequence of looking through that kind of Taylor expansion stuff and looking at the removable singularities, taking advantage of the removable singularity of the difference quotient to move on with this, is we found out that we could write f of z analytic in this as well, it has a bunch of zeros. So there's going to be z minus z1, and let's say there are n zeros, n roots. So z minus zn times some function g of z. And this function g of z is non-zero and analytic. It's really important that it's non-zero because in a second it's going to be on the bottom. And that's how I got this scar in 8th grade, so we don't want to go there. So that's the situation that we have with every analytic function as far as we can break it down and in the disk delta. Okay, so now we take this thing that you probably studied in calculus and went, well, when am I ever going to use this? Well, now's the time, so maybe that wasn't the time to study it. But what we're going to look at is what's called the logarithmic derivative. So that's the derivative of log f, and we've kind of arranged things so that we have a single branch here, but the derivative of log f isn't the issue, it's the integral. Anyway, that's f prime over f. That's just the chain rule. And this takes a different form. To be compact, I'm going to say, well, see, each of these factors, z minus z sub j or something, first of all, when you take the log, you get the sum of the logs of each of these. And when you take the derivatives of each of these, you just get one. That's the derivative of z minus z sub j over z minus z sub j. So you get an expression that looks like this. You get a sum of these little reciprocals, j equals 1 to n. And then you're going to have something that we're about to ignore in a responsible adult manner, which is g prime over z. So taking the log of all this, applied the chain rule, and so there's the derivative f prime over f. And What's interesting is if you integrate this, and I'm sorry I didn't leave enough room, but I'm going to try to squeeze it in. If you integrate both sides of this expression, so on the one hand you get this integral of f prime over f, and on the other hand you get this sum of a whole bunch of integrals. G of z is not 0. We made sure that we had that situation. So g prime over g is analytic, and when you integrate it, Cauchy's theorem, we're still talking about Cauchy's theorem, aren't we? Cauchy's theorem says that the integral of this around gamma, oh, it would be nice to have a domain for these integrals, wouldn't it? The integral of g prime over g over gamma is 0. It's analytic. And so what we're left with is, well, I'm just going to say goodbye, Mr. G prime over G. And so, so what we end up with is this expression, integral over gamma. Hey, you know what? Just for fun, let's put a 1 over 2 pi I in front of that because we're going to recognize something here. Of that fraction, top is f prime of z, bottom is f of z dz, is, now if we look at the integrals here, if we multiply that by 1 over 2 pi I, that's just the winding number of gamma around the point z sub j. So we're seeing the winding number. That's why we threw the 2 pi I in. So I'm just going to call this the sum j equals 1 to n of the winding number n of gamma z sub j. So this logarithmic derivative counts zeros. You can also do something about this with poles. So that might be something interesting to think about a little bit. But the logarithmic derivative counts zeros with, you know, it depends on what gamma is, but gamma is a closed curve, so that makes sense. So what we've done is taken the logarithmic derivative and used Cauchy's theorem to get the part that we don't really understand. Oh, that integrates to 0 anyway. Yeah, who cares? Okay, and then we end up with all these winding numbers. Now, if we want to change this around so that we're looking at, instead of where f of z is equal to 0, we look at where f of z is equal to a. So what we've done here is souped up what's on this parabola. Instead of looking for where the parabola hits the axis, we're going to move up a little bit. And so this is going to change our one point with multiplicity into two separate points. And so if we look at where f of z equals a, and we go through this whole process again, what we find is, first of all, that there are going to be n roots, so let's give those names. They depend on a, so I'm going to just call them the z sub j's of a. There'll be n of them. And you'll see if you have some doubt about that, you'll see why. And what we're going to see here is the sum of the winding numbers around the same gamma around these roots is 1 over 2 pi I times the integral over gamma, same gamma, of, and now the integral gets changed just a little bit. The top is still f prime of z, and the bottom is f of z minus a. And what we've done is we've taken the logarithmic derivative of f of z minus a, and when you take the derivative, the derivative of f of z minus a is still f prime. A is a constant, and so we get this expression here, and that shows us that and we know the winding numbers, as long as we're in the same region defined by the Jordan curve region defined by the curve gamma, then the winding numbers don't change very much. And so this is not going to change if you wiggle a little bit. And so the consequence of that is the Alfor's Theorem 11. And I'm going to state that a little bit roughly because you have a precise statement available. So if f of z equals w0 has a root of order n at z sub 0, so that's the situation that we're talking about, then well, for every epsilon there exists a delta. Careful, this is not a standard epsilon delta statement. For every epsilon there exists a delta with the property that if I wrote too small, a minus w sub 0 is less than delta. So if you're close, you don't expand out too far. I'll show you why in a second. You don't want to expand out too far. So if you stay close to the value that you're looking at, then that means that there are n distinct roots in the circle around z sub 0 of radius epsilon. So the reason that that's an issue is if we look at something more general, we could have the following situation where we need to limit the domain, because if we go out too far, we might start to pick up other zeros from other parts of the behavior of the function. So we don't want to do that. So that's why this domain gets limited. And there's the deal. And so that's a nice theorem. There's a corollary of this, which is the open mapping, that F is an open mapping. It takes open sets to open sets. And so that is something nice, that it takes open sets to open sets. And the reason is that you just keep you've got these neighborhoods defined by the previous theorem, and so everything becomes open. But this now leads to the following very profound consequence, and this is Alfors's theorem 12. So before I get on to theorem 12, I want to remind you where we started. We started in calculus 1, looking at what happens with multiple roots. And now we're going to get to something extremely profound, which is this. This is the maximum principle. And it's the maximally useful principle. And the maximum principle says that if F is analytic and non-constant, in some region omega, capital omega, then the absolute value of f of z has no maximum in omega. I'm going to write max because, okay, I'm taking longer to explain it than it's worth. And the reason is that you've always got an open set. I'm doing a real picture. So if you think this is the maximum, you've got an open set around the pre-image, and so that means you have an open set around the image, and so there are going to be points that are bigger than absolute value of f of whatever in that region, and so you can't possibly have a maximum in the region. This is kind of the inverse of Heine-Borel. So start with this very basic idea about looking at multiple roots. Throw in some stuff from Cauchy's theorem, and we really used Cauchy's theorem in an essential manner here and come up with this extremely profound consequence. This is one of the most important consequences in complex analysis. And by the way, this also then applies to the real and imaginary parts, and so you get the same consequence for harmonic functions.